What's up everyone, welcome back to my channel, and today we'll be kicking off a brand new series on a topic that makes a lot of chemistry students sweat, organic chemistry. Now before you stress out, let's clear the air. Organic chemistry isn't an impossible puzzle, and it's just the study of carbon-containing compounds. That's its whole secret. Carbon is unique because it can bond with itself and other elements to form an endless variety of shapes and structures. And in this video, we're going to walk through the complete foundation of organic chemistry together. We'll start with how to read the models on your screen, learn the rules for naming them, and wrap up by looking at the fundamental chemical reactions these molecules undergo. No matter if you're an absolute beginner or prepping for a big test, we're going to take this step by step directly from the slides. So let's flip over to the next slide and look at how we draw these structures. Look at the models on this slide. This is our very first major milestone, and that's learning how to look at an organic molecule on a page. Depending on how much detail we need, we can draw the exact same molecule in a few different ways. First, let's take a look at the full structural formula. This is a complete Lewis structure, and it explicitly shows you every single carbon atom letter C, every single hydrogen atom letter H, and every single solid line representing a covalent bond. While it's very detailed, it also takes a long time to draw out. If a molecule had 20 or 30 carbons, you would spend the entire exam just drawing straight lines and writing letters. So instead, to save space and time, look at how we can simplify it into a condensed formula. Instead of drawing out every single bond line to the hydrogens, we group them together. If a carbon is holding 3 hydrogens, we would just write CH3, and if it's holding 2, we would write CH2. It tells you the exact same structural story, but it fits perfectly on a clean line instead of text. Here, you have the Lewis dot diagram and the VSEPR representation of the correct bond angles, but we'll get back to that in a later video. Below that, the ball and stick and space filling diagrams are both ways of representing the molecule in 3D, with the ball and stick model showing you the bonds at the cost of the visual accuracy that the space filling model provides. Finally, at the bottom, we can look at the gold standard of organic chemistry drawings, which is the skeletal structure. It's the zigzag line you see at the bottom, and notice how the letters C and H are completely missing. So instead, to read this hidden code, you have to need 2 basic rules. Rule number 1, every single endpoint and every single corner vertex on the zigzag line is a secret carbon atom. They just don't want to write it all out because they're lazy. Rule number 2, carbon always wants to make a total of 4 covalent bonds to be stable. In a skeletal drawing, we only draw the lines between the carbons. Any leftover bond that you don't see is automatically assumed to be filled by a hidden hydrogen atom. So if a corner point has only 2 lines touching it, it secretly has 2 invisible hydrogens attached to it to hit that magic number of 4 bonds. Now that we know how to read the basic carbon lines, let's move to slide 3. This is our reference chart for functional groups. Now, pure carbon and hydrogen chains are generally unreactive, but everything changes when you drop in specific clusters of other atoms like oxygen or nitrogen. These clusters are called functional groups because they dictate exactly how the molecule functions and behaves. Let's go through some of the groups so you can figure out how to spot them. Let's start with the alcohol group. You can identify an alcohol by looking for an OH hydroxide group attached to a carbon, which is represented by R. Over to its right, look at ethers. An ether also contains a hydrogen, but notice the layout. The oxygen atom is buried directly in the middle of the chain, sandwiched between 2 carbon groups. Next, at any time you see a carbon double bonded to an oxygen, we call that a carbonyl group. If that double bonded oxygen is on the very end carbon of a chain with a hydrogen, it's an aldehyde. If that double bonded oxygen is at the end of the chain with 2 carbons attached, it's a ketone. If you see a carbon that has both a double bond to an oxygen and a single bond to a hydroxide and a carbon group, that combination creates a carboxylic acid. If that acid gets modified so that the hydrogen is replaced by another carbon chain, it becomes an ester. Finally, look at amines, which introduce a nitrogen atom into the structure. This whole table might seem generally overwhelming at first glance, but it's not your job to memorize all of these because over time you're going to train your eyes to recognize a bunch of special, more common functional groups that appear more often on the AP style questions. You're going to be able to spot the atom arrangement and you'll instantly know the molecule's family. And it's important because this brings us to our next slide, naming the roots. Now, in order to name the actual molecules, you need to know the rules behind nomenclature. Organic naming is beautiful because it works exactly like a puzzle. The very first part of a molecule's name is the prefix, and the prefix tells you exactly how many carbon atoms are chained together in the primary backbone. Let's look down the list on the slide. The first four prefixes are the unique ones that you need to commit to memory. A 1-carbon chain uses the prefix meth. A 2-carbon chain uses eth or eth. 3 carbons gives us prot, and 4 carbons gives us but. If you're a beginner trying to lock these 4 in without mixing them up, use this simple mnemonic device. Monkeys eat peeled bananas. Clever, right? Monkeys for meth, eat for eth, peeled for prop, and bananas for but. Once you get past 4 carbons, the prefixes become standard geometry terms that you likely already know. 5 carbons is pent, 6 is hex, 7 is hept, and 8 is oct, just like an octagon. So the second you see an organic name on a slide or an exam, your brain should immediately read that prefix as a direct counter for the carbon chain length. Once you know the prefix for the number of carbons, you need to look at the ending of the word, or the suffix. As you can see on the slide, the suffix tells you exactly what kind of covalent bonds are holding these carbon atoms together. Today we're looking at pure hydrocarbons, which are divided into 3 clean families. The first family is the alkanes, which use the suffix -ane. Alkanes mean that every single carbon-to-carbon bond in the entire molecule is a single bond. If you see nothing but single lines on your slide, it's an alkane. The second family is the alkenes, which use the suffix -ene. If you spot a double bond drawn as 2 parallel lines between 2 carbons, the molecule instantly becomes an alkene. The third family is the alkynes, using the suffix -yne. This means that there's a rigid triple bond, 3 parallel lines, sharing 6 total electrons between 2 carbons. Most of these are pretty easy to match to their functional groups, but cyclo means that the molecule forms in a carbon chain in a loop or ring shape instead of a straight line. So make sure you never mix these letters up on a quiz. Look at the neat alphabetical trick right here on the slide. Look at the vowels in order for the first 3. A, then E, then Y. Now look at the number of bonds in increasing order. 1, 2, and 3. It matches up perfectly, doesn't it? So A in ane is for single bonds, E in ene is second for double bonds, and Y in YNE is last for triple bonds. Now let's pull all these pieces back together and look at the official nomenclature rules used to name any compound systematically. When you're handed a structure, you always follow this exact step-by-step checklist on screen. The first thing you want to do is find the longest continuous chain of carbon atoms. This is called your parent chain. Be careful because this chain can twist and turn around corners on a skeletal drawing, and it doesn't always have to be a straight horizontal line. Now count the total carbons in that longest path to determine your root prefix from slide 4. Step number 2 is to number the carbon atoms in that parent chain. You can number it from left to right or right to left. The rule is that you must start numbering from the end that gets you to a branching point or a double or triple bond the fastest. We want the lowest possible numbers for our features. Next step is to identify and name any branching groups that are hanging off of the main chain, which we call substituent groups. Finally, you assemble the full name for the compound by listing these branching groups in alphabetical order, followed by your main parent chain prefix and suffix. By taking it systematically and following these rules directly from the slide, you can decipher the name of any foundational organic chemistry molecule seamlessly. Now that we completely understand how to read structures and name them, we are ready to move into the second half of our slideshow, which is organic reactions. Now, in general chemistry, you might be used to balancing reactions like single or double replacements. In organic chemistry, reactions look a bit different, however. Instead of swapping whole elements, we look at how functional groups get transformed, broken apart, or put together to form entirely new products. As you see on this overview slide, we're going to look at several fundamental types of reactions: substitution, addition, esterification, combustion, oxidation, and polymerization. For each reaction, your goal isn't to memorize random words, but rather to look at the structures on the slide and identify exactly what changed from the left side of the arrow to the right side of the arrow. So let's start with our first reaction on slide 8, which is substitution. This is a substitution reaction, and the name gives away the whole game here. Substitution means that you're taking one atom out and substituting a different atom directly into its place. Look at the chemical equation displayed on the slide. On the left side, we start with the saturated ethane and a bromine molecule. Notice what happens as we move across the reaction arrow to the right side. One of the hydrogen atoms attached to our carbon chain has been completely swapped or substituted out, and a bromine atom has taken its position. What happened to the hydrogen atom that got kicked off? Well, it actually pairs up with the second bromine atom to form hydrobromic acid as a byproduct. A key thing to notice on this slide is that the core carbon-to-carbon chain didn't break and no double bonds were created or destroyed. Literally, all we did was just trade the hydrogen for a halogen. Whenever you see an atom on a chain get cleanly swapped out for another one, you're looking at a classic substitution reaction. Now let's compare that to slide 9, which shows an addition reaction. This is completely different from substitution, and it relies entirely on the presence of an alkene. Look at the reaction on the left side of the slide. Notice that we have a carbon-to-carbon double bond. That second bond is rich in electrons and can be opened up like a gate almost. When we react the alkene with a molecule, for example, the bromine gas or another halogen, we don't swap anything out. Instead, the double bond completely breaks open and converts into a single bond. Look at the product side on the right. Because that double bond opened up, both carbon atoms now have a brand new open slot to form a bond. The two incoming atoms are both added directly into the molecule, one on each carbon. Notice that we went from an alkene with a double bond to a fully saturated alkane with single bonds. Nothing was kicked off or left over as a byproduct, and everything was added together into one single molecule, which is exactly why we call it an addition reaction. Now, for esterification, let's look at a specific and highly beautiful process that you see very often in your lives. Based on the name alone, you can already guess what the final product is going to be because we're making an ester. Let's trace the two starting ingredients on the left side of the slide. We're combining a carboxylic acid, remember from slide 3, that's a carbon double bonded to an oxygen and single bond to a hydroxide, with an alcohol, which is a carbon chain with a hydroxide group. When these two molecules collide right under the correct conditions, a specific piece gets chopped out. The carboxylic acid drops its hydroxide group and the alcohol drops its hydrogen atom. If you combine a hydroxide with an H together, what do you get? You get H2O, water. Look at the product side on the right. With the water molecule squeezed out, the remaining carbon chain from the alcohol links directly to the oxygen on the carboxylic acid. This creates a brand new ester linkage. Esterification is incredibly famous because esters are the molecules responsible for pleasant, sweet smells like fruits and perfumes. So every time you see an alcohol and an acid join together to create a sweet-smelling ester and kick off a molecule of water, you're looking at esterification. And now for a fun one. This is a reaction you're probably already familiar with from general chemistry, but it's a massive part of organic chemistry, a combustion reaction. Combustion is just the chemical term for burning a fuel in the presence of oxygen. Look at the reactants on the left side of the slide. We start with a hydrocarbon fuel, or a molecule made of carbon and hydrogen, and we mix it with gaseous oxygen, or O2. For a complete combustion reaction of a pure hydrocarbon, the products on the right side of the arrow will always be the exact same two things, carbon dioxide and water, alongside a massive release of energy in the form of heat and light. It doesn't matter if your starting fuel is a tiny 1-carbon methane molecule or a massive 20-carbon chain. If it undergoes complete combustion, it will consume oxygen and completely break down into carbon dioxide and water vapor. Whenever you see O2 on the left and CO2 plus H2O on the right, your brain should instantly flag it as a combustion. Now let's look at slide 12, which covers oxidation. In organic chemistry, this is a very simple practical definition for oxidation that you can spot visually on a slide without counting individual electron numbers. Organic oxidation simply means that we're increasing the number of bonds to oxygen or decreasing the number of bonds to hydrogen. Now let's look at the example on screen, the one that isn't completely reduced, so the second one on the left. We start with the primary alcohol on the left, and the carbon holding onto a hydroxide group, meaning it has one single bond to a hydrogen atom. Now look at what happens when we introduce an oxidizing agent. As we cross the arrow to the right, that single bond to oxygen is upgraded into a double bond to oxygen, forming a carbonyl group. Because we increase the number of shared bonds between that carbon and the oxygen atom, the molecule has been oxidized. Depending on how strong the reaction is, it can be oxidized even further into a carboxylic acid. When tracking organic charts, if you see a molecule gaining oxygen bonds or losing hydrogen lines, it's undergoing oxidation. And finally, let's wrap up with our very last slide, slide 13 for polymerization. This reaction is responsible for almost every plastic, synthetic fiber, and just material you see in your daily life. To understand polymerization, you just need to break down two words on the slide, monomer and polymer. Mono means one, poly means many. A monomer is a single, small organic molecule, usually an alkene with a double bond. Look at the visual on the slide showing these individual monomer units lined up next to each other. When we trigger a polymerization reaction, the double bonds inside these monomers break open, stretching out to the left and the right. Instead of adding a separate chemical like we did in some of our other reactions, these individual units use those open bonds to link directly to each other. Now look on the right example. Those small independent pieces have chained together to form a massive, repeating macromolecule called a polymer. It's like taking individual paper clips and hooking them together to make a giant chain. When you see small alkene units opening up their bonds to form a long, continuous, repeating chain, you're witnessing polymerization. And just like that, you've walked through the complete structural foundations, naming conventions, and fundamental reactions of organic chemistry directly from the slideshow. If this comprehensive slide-by-slide breakdown helped you feel confident and ready for your class in the fall, make sure to hit that like button and subscribe to my channel for more upcoming AP Chemistry content. Keep studying smart, and I'll see you guys in the next video. Thank you.